This video is about simplifying multivariable polynomials, which is really just the culmination of everything we've already discussed in terms of polynomials and terms and factors and exponents and all those things. So we're going to dive right in with some examples and apply all of our algebraic concepts. Our first example reads as follows. We have a set of parentheses containing 5x to the fourth y squared plus 6x cubed y minus 7y, close parentheses. Then we have a minus sign. Then another set of parentheses, these containing 3x to the fourth y squared minus 5x cubed y minus 6y plus 8x. Now, that's a lot to work with. So what we're going to have to start doing is observing the parentheses and what they are doing for us. Mainly, there are two important things to consider. Sometimes parentheses are holding an exponent on the outer right, side of them, as in the superscript exponent place. These do not have those, though. So there are no exponents outside of these parentheses. But the other key thing that parentheses can do is hold a negative sign out in front that would have to be distributed, which is the case in the second set of parentheses for this problem. So we're going to have to go ahead and distribute the negative sign to all the terms in the second set, which will, by the way, just change all those signs. And in so doing, we can rewrite the entire problem without any parentheses, which will allow us to move things around and combine like terms as needed. The first set of parentheses has nothing in front of it and no exponents, so we can just rewrite without them. We'll write it as 5x to the fourth y squared plus 6x cubed y minus 7y. Now we're going to continue with the distributing here, so we'll have minus 3x to the fourth y squared, and then a plus 5x cubed y, and then a plus 6y, and then a minus 8x. Notice all those signs now are different in that second set of parentheses. But now we have no parentheses, which means we simply want to combine like terms at this point. So look for matching. Remember, like terms have the same powers of the same variables. So if you look at the first term, which is a 5x to the fourth y squared, we'd be looking for another x to the fourth y squared to combine with it. It turns out there is one more down the line. It's the negative 3x to the fourth y squared, but that's the only other one. So to combine these terms, we'll simply add their coefficients. 5 minus 3 would be a 2. So we'll say 2x to the fourth y squared, and move on. So the next term we see is an x cubed y, and I'll do a different double underline for it because it's not like with the first pair we identified, but there's another one that will be like with this one. There's another x cubed y down the line. That's the positive 5 of them. So I have positive 6 and a positive 5 x cubed y. Put those together and you get a positive 11 x cubed y. And then moving on from there, we see a couple y terms. There's a negative 7y and a positive 6y, which together would create a negative 1y, or just a negative y. And then there's a minus 8x at the very end, which has nobody to play with. There are no like terms with it, so we just copy it in at the end. And this now is the result of combining all the terms that are like with the multivariable polynomials that we just discussed. Let's try another example, but this one begins a little differently. It has a wordy or verbal beginning. It says, subtract 23x minus 5y from the sum of 6x plus 15y and x minus 19y. So we have to translate these words into math carefully with a couple key phrases going on. When you see a phrase like sum of, you can immediately group whatever follows it. So sum of, I'm going to open a set of parentheses and then close them after it lists the two things we're going to sum, or in other words, add. So when it says sum of 6x plus 15y and x minus 19y, we're going to add those two expressions together. But before that, we saw a keyword subtract, and we have to keep the order carefully with subtraction because the order does matter. It says subtract 23x minus 5y from, so there's your key pairing of words, subtract from. So if you're subtracting from something, then whatever's after the from has to come first, which in this case is the sum of. So we're going to put the sum of these two terms, which is at the end of our little sentence here, first. I'm going to put 6x plus 15y plus x minus 19y. That's the sum refers to the plus sign we have in between those two expressions. There's the sum of those, but from that, so after it, we're now going to subtract 23x minus 5y. However, what I've written out as is not correct. You have to put that expression which we are subtracting in parentheses because in front of it is a minus sign, and that minus sign would have to be distributed to both of the terms in these parentheses now that follow. Once we do that, we should be able to combine like terms and finish from there. So let's go ahead and recopy everything we see so far. I'm going to just wait on combining like terms until we do the distributing for the negative, so we can do them all at once, though you could combine some things up here in front at first. If I distribute the negative, I'll then have a minus 23x plus 5y at the end. Now I'll look for like terms. I have a 6x in the front, a plus x, and then a minus 23x. Those would all be like, and we'll combine them by simply adding their coefficients. So really we have 6 plus 1. There's an invisible 1 in front of the plain x we see there. So that's 7, and then minus 23 would give us a total of negative 16x. So that's our x terms combined. Now we look for the y terms. We had a plus 15y, a minus 19y, and a plus 5y. If we combine those coefficients, positive 15 minus 19 would be a negative 4, plus 5 would be a positive 1, so we would just say plus y, or you could say plus 1y. So you could write it like that. You could write it as, sometimes you may not see the negative sign left out, flapping in the wind out front, so you might see people rewrite this as y minus 16x. It's the same thing, but that's our simplified answer. Our third example begins with a set of parentheses containing 7x to the fourth, y to the fifth, close parentheses, and then immediately next to it, so there's nothing in between, the next set of parentheses, which contains negative 10x to the seventh, y to the 11th. So the fact that there's nothing in between these parentheses is significant. That means that we're actually multiplying these two together. This would be considered a monomial times a monomial, a one term times a one term, if you apply all the definitions of terms and polynomials we've seen previously. And so if I multiply these together, notice every factor is simply being multiplied by the next factor, which means if all I have is multiplication going on, I can rearrange the order any way I'd like. Now you may say, well, I see a negative sign in front of the 10. Yes, but it's not subtraction because there's nothing in front of it, right? Which means I'm not actually subtracting. That's being used as the negative for the 10. Now, I can rearrange the order and multiply number with number. So 7 times negative 10 would give us a negative 70. Then I can multiply like bases together to utilize the exponent rules we know. X to the fourth times x to the seventh would be the rule where when you multiply the same base, you add the powers. So that'd be an x to the 11th. And then y to the fifth times y to the 11th, same rule. This would be a y to the 16th, adding the 5 and 11. So negative 70, x to the 11th, y to the 16th would be it. Our next example starts with a 2ab squared out in front of a set of parentheses, which contain 20a squared b cubed plus 11ab. Now in this case, we don't have all multiplication like we did in the previous example, because I have a plus sign with something on either side of it in that second set of parentheses, which means we would actually have to distribute the 2ab squared that's out in front of the parentheses into both of those terms inside. When we do that, we can use all of the exponent rules we know and multiply number with number and base with base that match. So in the first case, when I distribute 2ab squared into the 20a squared b cubed, I can multiply the 2 times the 20, which will give us a 40, the a times the a squared, which will give us an a cubed, and then the b squared times a b cubed, which would give us a b to the 5th. And that's the result of the first distribution. Now I add to get to the second one and kind of start over. So 2ab squared times 11ab would be 2 times 11, which is 22, a times a, which is a squared, and b squared times b, which is b cubed. And that would be our result simplified for the distributive property for this example here. Let's try another example. This one has a negative b out in front of it, and then inside parentheses immediately following it, we have a cubed minus ab plus b cubed. Now here we'll distribute like we just did in the previous one, but now we're distributing a negative b inside, which will change the signs of the terms as well as affect the actual terms because we're going to multiply by a b. So a negative b times a cubed would become a negative ba cubed. Of course, the order in which you write the a and the b doesn't matter. You could write the a cubed first and then the b, but the a is cubed, not the b. So we have negative ba cubed, and then plus, because a negative b times a negative ab for the second term here would be a plus ab squared. And lastly, a negative b times a positive b cubed would be a negative b to the 4th, simply adding the powers with the like bases multiplied together. And this could be our final result. All right, let's do one more example looking like these. This one contains two sets of parentheses. The first set has x plus 9y. The second set has 6x plus 7y. And these are being multiplied together, these parentheses, which means we could go ahead and use the FOIL process on this one. Notice it doesn't actually fit any of our special products that we've also discussed. It's not, for instance, a perfect square or a difference of squares, though sometimes those apply in this context. We're going to go ahead and just FOIL this out. First times first would be x times 6x. That would be 6x squared. Outer times outer would be x times 7y. That would be a plus 7xy. And inner times inner would be a 9y times a 6x. That would be a 54, so positive 54 xy. And last times last would be 9y times a 7y, which would be a positive 63 y squared. Now you'll notice after FOILing that the outers and inners produced some like terms. They both have xy involved with them. So we'd want to combine those to finish, which would result in 6x squared plus, this is positive 7 plus 54, so it'd be plus 61xy, and then plus 63y squared for our final result. Let's try yet another example, the next one. The best way to get all this is to do 100,000 examples, so which is why I'm doing so many. This next one begins as x minus y in parentheses, followed by another set of parentheses containing x squared minus 4xy plus y squared. Now we've actually seen a setup like this before, but it didn't have multiple variables, which is the point of this topic. So we're going to apply the same thing we know already, which is to distribute both terms in the first parentheses to all the terms in the second set. But we're going to do so carefully, knowing that we have different variables involved. So let's go ahead and write this out by first distributing the x to all the terms in the second set. So x times x squared would be x cubed. X times negative 4xy would be a minus 4x squared y. And then an x times a plus y squared would be a plus x y squared. Then we have to go back, as we've seen before, and distribute the negative y to all the terms which follow it. That would produce a negative x squared y, or you could say negative yx squared, same thing. And then a positive 4xy squared, and then a negative y cubed. Distributing the negative y into all three terms in the second set of parentheses. Once everything is distributed, which can be quite a bit, as we've now seen, you have to make sure and not do something twice accidentally and not forget anything. We want to look for like terms to combine. Notice I only have a single x cubed, nothing else to combine it with, so I'll just leave that alone out in front, x cubed. My next term has an x squared y, but there actually is some more of that. So I have an x squared y, and then down the line an x squared y, negative x squared y, and actually that's the only two. So I could combine those to get a negative 5x squared y. Then I'll notice we have a plus xy squared, and there's another one of those as well, plus 4xy squared. So together that'd be a plus 5xy squared. And then at the end we have this lonely minus y cubed with nothing to combine, so we'll leave that alone as part of this combined answer at the end. Okay, let's go on to the next one we have listed here. This one begins with a set of parentheses that are squared. In these parentheses we have x squared y squared minus 3. And again, that's all being squared. Now, we have to be careful with this. There are two ways to do this. And one way would be to use these special products that we've already discussed earlier, and the other way would be to FOIL this out. It seems common that students forget the special products formulas and would have to rely on FOILing this out, but it's also very common in this particular kind of example for a very big mistake to occur, and that is sometimes students will say, hey, let's distribute this power of 2 inside. That's an absolute no. Does not work. We've talked about this as a big warning in a previous video. When you have a subtraction or a plus, really, connecting terms inside parentheses, you cannot distribute a power across those. So do not do that. Rather, we're going to either use a special product or just expand this out. I'm going to go ahead and just expand this out since I think that's probably the most common way students at this level would approach it. So x squared y squared minus 3 times that very thing, x squared minus 3. Now, the point here is we'll have to FOIL those together. And to do so, we'll see first times first would end up being an x to the 4th, y to the 4th. Outer times outer would be a minus 3x squared y squared. But then inner times inner would be the exact same thing, minus 3x squared y squared. And then the last times last would be a plus 9. You'll notice a couple like terms to combine the outers and inners. Sometimes that happens. So we'll combine those for our final answer and get x to the 4th, y to the 4th, minus 6x squared y squared plus 9 is our final result. Now, there's another example I want to discuss here, and this last example for this topic, has a new scenario. This is a 3-term trinomial times a 3-term trinomial. So it does not fit the FOIL, which is a 2-term times 2-term. And we've seen 2-term times 3-term above, but now we're seeing 3-term times 3-term. So you just have to distribute everything in the first set of parentheses to everything in the second set, which is a lot, and it's easy to get lost on doing something twice or forgetting part of it. But if we stay organized and careful, I think we'll be fine. I'm going to start with the x, the first term in the first set of parentheses, and distribute it to all the terms in the second set. Well, x times x would be x squared, x times negative y would be negative xy, x times 1 would be a plus x. Now we back up, take the second term, and distribute it to all the same terms in the second set of parentheses. So y times x would be a plus xy, or a yx, the order of those doesn't matter. And then y times negative y would be a minus y squared, and then a y times 1 would be a plus y. Then we'll move on to the last, the plus 1. If that gets distributed to all the 3 terms after it, we'll just have plus x minus y plus 1, doesn't change anything there. Then we look for like terms to combine. Notice we have an x squared, but there's no other x squared term. So we'll just copy that one down in front. I have a minus xy, secondly, and then a plus xy a couple terms after it. Those would actually cancel right out. They're like terms and they would disappear, turning into 0xy, which is just 0, doesn't even show up. Then we'll look and notice there's a single x plus x, and then there's another single plus x down the line. Those would combine to be plus 2x, but there's no other like term with those. Moving on, we have this minus y squared. There's no other y squared, so we'll just copy that down in place. Then we have a plus y and a minus y that would cancel, and then we have a plus 1 at the end. So altogether we have here x squared plus 2x minus y squared plus 1. Now the order of that could vary as far as the way you write it out. I just kind of picked a natural order going left to right here, but you could actually shuffle the order of some of these and maybe even go further in some cases, which we'll see later on in the factoring topic. But for now, we can leave it right here.